What I want to do now is wrap up the Java monitor object discussion, kind of put it all in context. So we'll talk about some of the usage considerations for Java monitor objects, and we'll particularly talk about some of the traps and pitfalls of using Java's built-in monitor objects. There's some tricky things that you have to be aware of and be careful of when you're programming with monitor objects. So here are some of the issues you have to be aware of. First, monitor objects are somewhat limited for a variety of reasons. For example, there's no support for non-blocking acquisition into the entrance queue. You have to wait, unlike reentrant locks. They also don't have timed or interruptible access into a monitor object. You're sort of in there until it decides that you get your chance to run. You can't time out. And once you're waiting to get in, you can't be interrupted. All those things are deficiencies which are addressed by other mechanisms like the reentrant lock. Another tricky issue is that synchronized statements, which are a piece of what a built-in monitor object does, have to support scoped locking. So when you come into a synchronized statement or synchronized block, the lock will be acquired, and when you leave that block, the lock is released. Now, at first glance, that may not seem like a big deal, but it turns out that for certain algorithms, this will end up complicating the implementation and potentially making it a bit more inefficient. And a good example would be the assignment that you're working on now, which relates to the specific notification implementation. The undergrad version is a bit more complicated than the grad version because you can't hold that lock over calls to a function or a block. In contrast, the grad version, which uses reentrant locks, can keep the lock held across function calls, which makes things more optimized and arguably a little easier to understand, but certainly more efficient and has less code involved. Another problem that we have with built-in monitor objects is there's no support for sensible timed waits. So there's a timed wait operation that's part of the wait queue mechanism, but its return value makes no sense, and it doesn't really tell you what you need to know. So using timed waits is tricky with the wait mechanism that's built into the wait queue of a Java built-in monitor object. That problem is also solved with Java condition objects, which are much cleaner and have more sensible timed wait semantics, where it returns a Boolean and indicates whether it timed out or not, whereas the Java version doesn't do that. There's also only one wait queue and one entrance queue, and that turns out to be problematic in a variety of ways. It's most commonly problematic for the wait queue part, but it's also going to be problematic for the entrance queue. So because of this, you could often end up with something that's called nested monitor lockout. And here's one of the situations where this occurs. Check this out. This is undoubtedly something that you will run across in your implementation if you're not really careful of assignment 2B. So here we have a class called buggy lock, and inside of it, it has an object, which we're going to call monobj. We could call it whatever we wanted to. And then we have a Boolean that says whether we're locked or not. So here's the lock mechanism. So the lock mechanism, which is a synchronized method, comes in here, and it says while locked, in other words, while this thing is true, while we're locked, we're going to go ahead and synchronize on monobj, and then we're going to call wait. But notice what happens when we synchronize on monobj, the intrinsic lock that's part of buggy lock is still held, because this is a synchronized method. And so as a result, if someone comes down here and tries to unlock this buggy lock object, it's never going to be able to get in to the critical section because we've gone to sleep with the intrinsic lock held. So that's what's called nested monitor lockout. And that's a subtle problem, and you may very well have run into it in your testing. So make sure you don't hold the intrinsic lock when you go to sleep on another nested object. So you can see it's nested monitor. That's why it's called nested monitor lockout. I should also mention there's other problems with there being one entrance queue. Most notably, you can't use algorithms that want to differentiate between different conditions in order to be able to allow multiple things into the critical section if they're disjoint. So that's another problem. choosing between notify and notify all is very tricky. And this is a very good link to take a look at for an excellent discussion of what the problems are. I think Zhao asked a very good question last time about the producer-consumer example I showed you. And her question was, why do we need to use notify all when it's not the case that you'll ever be waiting explicitly both for the queue to be empty and the queue to be not empty, or the queue to be not empty and the queue to be not full? You'll never be waiting for both of those conditions at the same time. And this link here has a very detailed analysis showing why you can still end up with deadlock even if that's the case. The thing to remember is you can only use notify if you have uniform waiters. They're all waiting for the same thing, so all things that can wait for the same thing. And you only want to notify one entity that wakes up. If both of those conditions hold, then you can probably use notify. But it turns out that you almost always need to use notify all for the reason that's discussed here in this article. Now, having said that, if you can't use notify, you should use it because that avoids the thundering herd problem. Even better is not to use Java built-in monitor objects for waiting notifying, but instead to use Java condition objects. That is a better solution overall. And notify all is there because we have to wait for different conditions. You have to wait for not empty and not full, for example. Another tricky part has to do with what we've been talking about before, these fairness issues, because there's no specification of when or which thread is awakened when things are notified. That's called haphazard notifications we've talked about. And you can use the specific notification pattern to control the ordering as we've described. And what that does, as you know, is make it programmatically clear which thread gets awakened if you have multiple threads waiting. That, of course, is more complicated as well. Often you need more than what's provided with built-in monitor objects. Built-in monitor objects work for very, very simple use cases, but as soon as they're anything more than just real simple stuff, they get too complicated for their own good. Classic example where simplicity in one level leads to complexity when things are composed. Very common problem in software design. So there's lots of other stuff in Java concurrent and Java concurrent locks and so on that you can use instead. Typically, reentrant lock and condition object are the way to go. Android provides other concurrency frameworks, which we'll talk about later. And if you use them, then what you do typically is you pass messages back and forth. And as a result, you often don't have to have monitor object or even synchronization semantics in your application code at all. In fact, if you look through the Android source code, which is a lot of fun to look at, and you search for the use of monitor objects, you'll see that they're very, very infrequently used. Especially the wait and notify mechanisms and monitor objects are almost never used in Android source code. And that's because they do message passing using the Hammer and async task frameworks in order to get around the need to share the variables through some other means, which is kind of interesting. Okay, so that basically wraps up this section on monitor objects.